Hey everybody, so in this video we are going to pick up talking about confidence intervals. Now we're going to take a look at constructing a confidence interval for a single proportion. We have been working with means up until now. And so the example that we're going to work with in this video is corresponding to a survey that was done in the spring of 2021, where they were trying to gauge how likely people in the US were to get vaccinated as the vaccines were becoming available to the public. And so let's say we want to come up and construct a confidence interval to approximate what proportion of all adults in the US do not plan to get vaccinated. And so looking at the table, that would be all of these people over here. And this corresponds to a proportion from the sample, which is 0.29. And the value that we're trying to approximate here is the proportion of all adults in the US that are not going to get vaccinated, and that we don't know. So in this video, we'll walk through how to construct a confidence interval to estimate this unknown population proportion. And so the good news with how we are going to construct these confidence intervals for proportions is that we are just going to extend the way that we did this with means to the same situation for proportions. And so recall that with a mean, we have the following situation where the sample statistic, our point estimate, is the sample mean. The z alpha over 2 we get depending on the confidence level. And if we know the population standard deviation, then the standard error would be the sigma divided by the square root of n. And the population parameter that we use this for to estimate would be for a population mean, which we denote with mu. And recall that this standard error formula we get from the central limit theorem for sample means. So let's recall what the central limit theorem tells us about proportions, namely, if we want to look at the distribution of sample proportions from some population that has proportion p, then it's going to be centered at the population parameter p, and the standard error we derived is equal to this formula over here, where n is the size of our samples. So we're just going to use the same approach that we used with means. However, we're going to replace what we use for the sample statistic and what we use for the standard error. So instead of x bar, we're now going to use the sample proportion that we calculate. So this would be the 29% of the people in the sample that said they would not get vaccinated. And then we use the same z alpha over 2 because this sampling distribution is also normal. And now we're just going to replace what we used for the standard error with means for what we know the standard error is for a proportion. And if you look at this formula, we have a bit of a conundrum here because we're trying to estimate p, yet the standard error depends on p, which we do not know. So let's think about how we can account for this unknown value p in order to come up with a calculation for the standard error. So we are constructing a confidence interval for a single proportion, and we'll see there are different ways that we can do this. This method that I'm talking about first is what's called the Wald confidence interval. And so here is what the confidence interval would look like in theory. And again, the problem here is we don't know what the population proportion p is, so we can't calculate this standard error. But we're going to do the typical thing, which is we are going to use the plug-in principle, which says, well, if I don't know what p is, let me calculate the corresponding statistic from our sample, which would be the sample proportion p hat. And I'm going to use that in place of p in my formula over here. And this does introduce a little bit of inaccuracy in this estimate. And we'll talk about how we can improve on this in a little bit. But it's not going to cause too much trouble. The distribution is indeed going to be very closely normally distributed, and that's why we're going to use the normal distribution to find the z alpha over 2. And so before we return to this example about vaccinations in the US, just take a look at this formula, and hopefully you see the similarity with this formula with the one that we used for means. Sample statistic, this term over here is going to be our margin of error, which is the z alpha over 2 times the standard error. And this is the main difference, which is how are we computing the standard error when we're looking at sampling distributions for a proportion. So on the next slide, we are going to work through an example and calculate a confidence interval for this proportion. So the goal is to estimate what proportion of all adults in the US are not planning to get vaccinated. And so based on this sample, our sample consisted of 1,082 adults. And from that sample, we found that 29% of them said, no, I am not planning to get vaccinated. And we want to come up with a 95% confidence interval. And so now we've got all of the information that we need. I know what my value is for p hat. That's that 29%. So those are going to go in each of these places. We know what the value of n is. That's 1,082. And based on the confidence level, we can figure out what these scaling factors, these z alpha 2 values, would need to be. Namely, we have that p hat. We want to write this as a proportion, which is going to be decimal 0.29. We have our sample size, and then z alpha over 2 for a 95% confidence interval. Recall, we're going to get approximately to 1.96 as the value for z alpha over 2. And so then we just plug all of these values into the formula. And that's going to give us p hat 0.29 minus z alpha over 2, 1.96, times the approximation for the standard error by plugging in the sample proportions. That's going to be the square root of p hat times 1 minus p hat, all divided by 1,082. And do not underestimate this calculation. It is a lot of operations that we want to do in the appropriate order. And this comes out to approximately 0.2630. So this is going to be our lower cutoff for our 95% confidence interval. And just want to mention that this term over here, the amount that we're subtracting from the point estimate, the 0.29, to get the lower cutoff for this confidence interval, this would be the margin of error on this estimate. And then we do a similar calculation to get the upper estimate, but now we're going to add the margin of error, but the margin of error is the same. And now we've got our 95% confidence interval, namely we have a lower of 0.2630, and we are estimating that this proportion is somewhere between that lower value and the 0.37170. So in other words, what this is telling me is there is a 95% chance that, again, we're going to attach this uncertainty to the interval. So there's 95% chance that the interval from 0.263 to 0.317 contains the actual proportion of all adults in the US that are not planning to get vaccinated. So let's summarize the method that we used to construct this confidence interval in the previous example. And so this method is what's called the Wald confidence interval. And for this method, the tricky part is we want to approximate this standard error. So the Wald confidence interval says we are going to plug in p hat in place of p when we are trying to estimate what the value of the standard error is. And this method has some drawbacks. The nice thing is we can do this by hand. We didn't take too long to calculate that in the previous example. But the downside is we're going to lose some accuracy when we come up with this approximation for the standard error by simply plugging in p hat in place of p. And so another method which is a little bit more accurate is what's called the Agresti-Coull confidence interval for proportion. And it's going to be very similar to the Wald confidence interval, just our point estimate and what we plug in for the population parameter when we calculate the standard error is going to be an adjusted sample proportion. So if we let x denote the number of successes in our sample, which in this case we have a sample proportion of 0.29, so then x would be the 29% of the sample of 1,082 people that said they were not planning to get vaccinated. So that works out precisely to 313.78. we can't have 0.78 of a person say they're not going to get vaccinated. So that this 29% from the sample was probably rounded. And so if we let x equal 314, we'll see that the 314 out of the 1,082 gives us 29% 0.02. So 29.02%. So that's where this 0.29 came from. So we're going to round up, since x should be a discrete value, should be an integer. So we're going to round up to 314. So that's what this value x is denoting. And so in the Agresti-Coull confidence interval, rather than use the sample proportion p hat, we are going to use what we're going to call p tilde. So this little squiggle above the p, we'll call it tilde. And what we're going to do is we are going to add 4 observations to our sample. So in other words, we're going to pretend that our sample consisted of 1,086 people. So we add 4 people to our sample. And out of those 4 people that we're going to add to our sample, we are going to assume that half of them are successes and half of them are not. So out of these 4 people, we're going to assume 2 of them said they were not going to get vaccinated. So that adds 2 to this count. And the other 2 said they were going to get vaccinated. And so now taking this adjusted number of successes and dividing by this adjusted population sample size, we get p tilde, which is going to be x tilde, x plus 2 divided by n tilde, n plus 4. Otherwise, the formula is the same. So we're using the same exact formula for the Wald confidence interval. We are just introducing p tilde, and we're going to place p tilde in place of every p hat that we had in the Wald confidence interval. And the other change is in the Wald confidence interval, we use our original sample. And now when we're using the Agresti-Coull, we use the adjusted number of observations and tilde, which is going to be 4 more than what our sample actually has. So on the last slide, we are going to create a confidence interval for the same proportion, what proportion of all adults are not planning to get vaccinated. But instead of using the Wald confidence interval, we're going to use this adjusted method, which is a little bit more accurate, the Agresti-Coull confidence interval. Okay, last slide. So now let's redo this confidence interval using the Agresti-Coull confidence interval. So instead of using p hat as 0.29, we have an extra step, which is we need to first calculate what p tilde is and then plug it into the same formula. So p tilde is going to assume we have 4 additional observations from the 1,082. And out of those 4 additional observations, half of them are successes. So we're going to add 2 to this 314. So after this adjustment, adding 2 to the successes, adding 4 to the observations, calculating this new proportion of 316 over 1,086, we get a value for p tilde, which is 0.291, right? Pretty close to p hat. And now the only difference is here I just pasted in the calculations that we did originally with the Wald confidence interval, where we used the 0.29 over here. And so recall that we are going to make 2 changes to our previous calculation. One is we're going to replace all of these p hats, these 0.29, with p tilde. Very close, but it'll make things a little bit more accurate. And we're also going to replace the original value for n with n tilde. And let me save these cutoffs. I just erased them, but let me save the cutoffs that we got for the Wald interval so that we can compare them to the Agresti-Coull. And I should mention as well that the 1.96 hasn't changed because we're still using a 95% confidence interval. So now I'm just going to replace all of the p hats with p tilde 0.291, all of the n's with n tilde 1,086. There we go. And after substituting in place the 0.291 and the 1,086, we get a lower cutoff, which is 0.264. And similarly, we get an upper cutoff, which is 0.318. And so now we can compare this with the Wald confidence interval. And we can see it's not much of a difference, but the Agresti-Coull is going to be a little bit more accurate. It's just shifted the Wald confidence interval just ever so slightly. And in case you're wondering, why is the Agresti-Coull more accurate than the Wald confidence interval? So these are two different estimators for the population proportion that we're plugging in to calculate the standard error and to give our point estimate. And this estimator is an unbiased estimator. This estimator, I lost a plus here, is actually a little bit biased, but it's more efficient. So for values of P, for if the population proportion is not very extreme, so if it's not close to 0 or if not really close to 1, which is most of the time, then this estimator, though it is biased, it's not biased as n gets really large, and also it has a smaller mean square error. So for that reason, this P tilde is in some sense a more accurate estimator to use than the P hat. Okay, so in this video, we looked at how we can construct a confidence interval for a single proportion using two different methods, the Wald confidence interval and the Agresti-Coull confidence interval. So on your quiz for next class, you'll have to practice these two methods. And when we start in class, we'll talk about how we can use R to calculate this and what we do when we have a difference of two proportions that are picked from two different populations.